My name is Zhe Lai. I was born in Kaohsiung, Taiwan in 2000. I am a student member of IEEE and currently pursuing a Bachelor of Science degree in Electrical Engineering from National Hsueh-Hsien University in Kaohsiung, Taiwan. My current research interest is the application of non-intrusive circuits to renewable power networks. My topic is transmission line fault location identifications in high-voltage transmission networks and different medium voltage wind farms using non-intrusive monitoring techniques. I've divided my presentation into 6 parts: introduction, background, proposed approach, study environment, simulation results, and conclusion. First, let me introduce the research. Nowadays, wind power is one of the most famous renewable energy sources in the world. However, we found that the present large-scale wind farms have some potential problems, such as grid faults, system stability, and blackouts. To solve these problems, we use non-intrusive fault monitoring to identify grid faults and enhance the system's stability. Professor Zhang has proposed the best method to recognize grid faults, which are using power spectrum-based hyperbolic S-transform. The method applies to the power transmission networks. Besides, many researchers have investigated different protection, comparisons, and improvements of grid faults for wind farms. Professor Hsueh-Hsien reviewed distance protection during balanced faults for the transmission lines connected with the wind farm's induction generator. Professor Dan and Chen proposed a fault write-through of DC offshore wind farms to minimize the transmission system's disturbance between the DC offshore wind farm and the AC grid. Professor Yao suggested balancing a hybrid wind farm capacity between a fixed-speed induction generator and a permanent magnet synchronous generator. Professor Kendukuri proposed a scheme to detect and classify wind turbine pitch resistance faults using three-phase motor currents. The research also shows that the extended Parkes vector modulus can diagnose the faults for both permanent magnet synchronous machines and induction motors. To find a rapidly real-time scheme of detecting and classifying transmission line faults for submarines, Professor Wang proposed a method to combine waveless noise reduction, Clark transforms, Stockwell transforms, and decision tree. Professor Yang analyzed the internal overcurrent faults of the DC transmission systems for the small-scale multi-voltage source converter DC wind farms and multi-voltage source converter high-voltage DC offshore transmission systems, using synchronized phasor measurement units. Professor Nayak studied a wide-area protection approach to quickly identify the paths closest to the faults. Professor Biswas proposed fault detection and classification methods using the sign of the change of positive sequence currents. The optimization algorithm is significant to minimize the amount of phasor measurement units in wind farms, due to the expensive cost and complicated placement of the synchronized phasor measurement units. Professor Zhang proposed a transient energy method to enhance the non-intrusive load identification accuracy and computational speed. To recognize non-stationary transient signals, he utilized a turn-on transient characteristic response of home appliances. Professor Zhang proposed an energy spectrum of the wavelet transform coefficients using Parseval's theorem for non-intrusive fault monitoring to represent low turn-on and turn-off transient features without demoting performance. Professor Zhang utilized Parseval's theorem and multiclass support vector machines to quantify different fault locations' energy distribution and obtain fault location identification in power transmission networks, respectively. There are two main approaches of our research, which are energy spectrum-based hyperbolic S-transform and support vector machines. First, I'm going to introduce energy spectrum-based hyperbolic S-transform. A continuous time signal S of t is derived by the continuous wavelength transform as the following integral. Furthermore, G of Tf is as the following equation. Stockwell transforms employs a scalable Gaussian window to provide a time-frequency space for false localization to solve the problems of non-stationary and transient signals. It is formulated as the following integral. In this equation, tau is a constant of phase correction on the time axis for the Gaussian function, and f is the frequency. Equation 4 is a general Stockwell transforms by utilizing a generalized window function. The generalized window function is equation 5, where p is a parameter of the shape of the window function. Equation 6 is the generalized hyperbolic S-transform. A hyperbolic window is used instead of equation 5 to form the generalized hyperbolic S-transform from a general Stockwell transforms to enhance the generalized window's resolution as high-frequency contents of false transients. Equation 7, 8, and 9 shows the detail of the elements of the generalized hyperbolic S-transform. In these equations, c squared is a positive curvature constant. HF and HB are two hyperbolas for forward taper and backward taper constants, respectively. A matrix of the particle features S of n-PL is formed by the hyperbolic S-transform from the discrete signals S of n-PL. In this matrix, I is the number of the data samples for each phase P at each location L, and J is the number of scales. The equation on the right side of the 11th expresses the arithmetic mean of the square of 10th as the time-frequency domain. Hence, equation 12 represents the energy spectrum of the 10th for each scale. Besides, k is the total number of data samples for each scale j. There are distinct false current waveforms for 0 and 180 degrees from figures 2a and 3a. They are respectively measured on S-bars for false locations ZL5 and ZL7 when the system yields a single line-to-ground false on phase A. Figures 2b and 3b show that the energy spectra are similar for the given signals of different false inception angles for false location ZL5 and ZL7 respectively. Figures 4a and 5a show different false current waveforms with three system voltage amplitude magnitudes -20, 0, and 20% of single line-to-ground faults on phase A, monitored on S-bars for false locations ZL5 and ZL7 respectively. Figures 4b and 5b show that the energy spectra are similar for the given signals of different system voltage amplitude magnitudes for false locations ZL5 and ZL7 from figures 2 to 5. The methods proposed by the authors have proved that particle features do not be affected by the different false inception angles and different system voltage amplitude magnitudes. As demonstrated in Figure 6, they are the energy spectra of three transmission line false locations, which are 05, 07, and L1F5 in 2 MV waveforms and 1 HV power transmission network, respectively. The other primary approach is support vector machines. A library of support vector machines utilize the one-against-one algorithm for multiclass classifications. We used the library of support vector machines to classify transmission line fault locations. The classification accuracy of the library of support vector machines is calculated by the following equation 13. Then I'm going to introduce our study environment. The proposed non-intrusive monitoring system comprises one equivalent power utility source and 7 transmission lines. The transmission line design for L1 and L2 between bus 1 and bus 2 is a mutually coupled double circuit line. L3, L4, L5, L6, and L7 designed as lumped parameter models for respectively contacted between L1 F3 and bus 3, between bus 2 and bus 4, between B3 BKL and bus 5, between L2 F5 and bus 6, and between B6 BKL and bus 7. Three synchronous motors modeled as the SM2, SM3, and SM4 are contacted with bus 4, bus 3, and bus 6. Two of four doubly fed induction generators rated 3.88 MVA associated with bus 5 and bus 7 through a step-up transformer. The library of support vector machines targets output of the false events are located on the nodes L1, F5, 05, and 07. Figure 7 illustrates the structure of the protection block diagrams. There are two main elements of Figure 7. First, the dataset consists of 1,961 samples obtained during 0.3 seconds. In a grounded fault, regarding a varying inception time from 0 to 360 degrees as intervals of 10 degrees for each fault resistance, and a changing fault resistance from 0 to 100 ohms as regular intervals of 10 ohms. We compared the results of our proposed method with other methods, such as the energy spectrum-based Stockwell transforms, change of the signal energy-based hyperbolic S-transform, and energy spectrum-based wavelets transform. The first row of our table shows different methods, and the first column represents the comparisons between these methods. So as shown in the table, we can see that energy spectrum-based hyperbolic S-transforms and energy spectrum-based Stockwell transforms results of SLGF AG of accuracy in cross-validation and classification are better than others. Furthermore, the outcomes from tables 1 to 10 are similar in that energy spectrum-based hyperbolic S-transforms and energy spectrum-based Stockwell transforms results of accuracy in cross-validation and classification are better than others. Energy spectrum-based hyperbolic S-transforms and energy spectrum-based Stockwell transforms results of SLGF-CG of accuracy in cross-validation and classification are better than others. In Table 4, energy spectrum-based hyperbolic S-transforms and energy spectrum-based Stockwell transforms results of DLGF ABG of accuracy in cross-validation and classification are better than others. In Table 5, The energy spectrum-based hyperbolic X transforms and energy spectrum-based Stockwell transforms results of DLGF-BCG of accuracy in cross-validation and classification are better than others. In Table 6, the energy spectrum-based hyperbolic X transforms and energy spectrum-based Stockwell transforms results of DLGF-CAG of accuracy in cross-validation and classification are better than others. In Table 7, the energy spectrum-based hyperbolic X transforms and energy spectrum-based Stockwell transforms results of DLF-AB of accuracy in cross-validation and classification are better than others. Table 8 shows that the energy spectrum-based hyperbolic X transforms and energy spectrum-based Stockwell transforms results of DLF-BC of accuracy in cross-validation and classification are better than others. Table 9 shows that the energy spectrum-based hyperbolic X transforms and energy spectrum-based Stockwell transforms results of DLF-CA of accuracy in cross-validation and classification are better than others. Also, in Table 10, we can see that the energy spectrum-based hyperbolic X transforms and energy spectrum-based Stockwell transforms results of LLLGF ABCG of accuracy in cross-validation and classification are better than others. So it is clear to show apparently that change of the signal, the energy-based hyperbolic X transform and energy spectrum-based wavelet transform values are smaller than those of energy spectrum-based hyperbolic X transform and energy spectrum-based Stockwell transforms of various false types in the cross-validation and classification accuracy. The tables also shows that the cross-validation accuracy values of energy spectrum-based hyperbolic X transform and energy spectrum-based Stockwell transforms are above 98.21% and 98.80%, and the values of classification accuracy are respectively above 93.93% and 93.33% for different fault types. Because of the tables, we can realize that both hyperbolic X transform and Stockwell transforms are better than wavelet transform for analyzing the characteristic transient current signal for false events in NIFM applications. In addition, the maximum classification time of energy spectrum-based hyperbolic X transform is smaller than 0.19 seconds for 1,830 examples. Hence, the time for each example is about 1.07 times 10 to the power of -1 millisecond. In the end, I want to conclude my presentation with 3 points. First, unlike phasor measurement units installed on each high voltage or medium voltage bus, the non-intrusive fault monitoring system removes intricate communication and synchronization time. Second, the proposed system can classify the various transmission line fault locations in high voltage transmission networks and different medium voltage waveforms. Third, the classification accuracy can be above 93.93%, and the classification time for each example is about 1.07 times 10 to the power of -1 millisecond. Thanks very much for your listening.